Greetings and welcome, friends. My name is Mr. Waddy. I'm here to teach you about geometria. Nope, sorry, my throat was a little dry. Geometria, there we go. We're in section 4.4. We're talking about congruent stuff. It's going to be great, just you wait. So here we go. It says two geometric figures are congruent. Now, we've only used the word congruent to apply to figures that were angles. We've applied the word congruent to figures that were segments, and now we're applying it to entire shapes, which entire chapters of our book will be regarding proving quadrilaterals congruent, proving triangles congruent. It's going to be a good time. And so here, this is like el más importante. It says two geometric figures are congruent if and only if there is a rigid motion or a composition of rigid motions that maps one of the figures onto the other. And then here's a big idea. Congruent figures have the same size and shape. Okay? So, same size and shape. Later on, we'll talk about similar figures which have the same shape but are like shrunk down or scaled up. All right, but right now we're talking about congruent. Good times, good times, good times. So let's take a look at example 1 here. Ooh, wow, I love these. These colors just remind me of like Mass Effect with like the orange holographic, sort of thing going on with the black. It's just amazing. I love it. So it says, identify any congruent figures in the coordinate plane. Explain. All right, does anyone have a suggestion of a pair of congruent figures? Yes, Josh.
IHJ and STU are congruent.
So let's see, I'll label that triangle IHJ, you are arguing, is congruent to triangle STU, triangle STU? We call it STU? Yeah, we'll call it STU. So let's see. All right. I'm digging that. Let's see. So IHJ, this is the claim. This guy is congruent to STU over here. All right. Do you have any support for that? What are your thoughts? Is there a transformation that you think you could describe, or you just? I think. Let's see. It looks like it might have been a 180. Yeah, I think J would have mapped to you. Let's see. I either could have described it as a 180 rotation, right? 180 degree rotation about the origin. Is there another transformation that you could have used to describe it? Anybody else? Let's see. You see, I've selected my color, which I don't know if... maybe you see what I'm doing here. Jack, what are you thinking? Yeah, this is the line y equals x. I love it. And it looks like this is equidistant to that. It looks like, yeah, 1, 2, 3, 4 diagonals, 1, 2, 3, 4 diagonals. It looks like, and depending on which one I selected, we actually would have had a different corresponding parts that we would have described as congruent. This one ended up being an isosceles triangle. So that's why there was more than one way to think about it. But that's cool, that's cool. All right, it's also possible I could have viewed it as a composition of transformations. I think if I mirrored it over the y-axis and then over the x-axis, it would have gone flop and flip, and that would have been pretty cool too, like so. Let's see, anyone have another suggestion for some congruent figures? Anyone other, let's see, oh, Anthony, what do you think? Let's see, bad k, yeah. Bad k is congruent to, what do we call this? Knurk. All right, there we go. Okay, all right. Let's see. Now, I arranged this in a particular way. There were a lot of different ways that I could have done it. What is the transformation you think that would have gotten this one to that one? Yeah, it went down. So like, let's see, it went down this far and then over this far. Anyone think they could label that as a I don't know, a vector in component form? Negative 2, comma, 1, 2, 3, 4, 5, 6. Yeah, negative 2, negative 6. That's the vector in component form. Well done. Yeah, high fives are appropriate. Yes. We also, oh yeah, oh, thank you. Yeah, high 10, represent. We also could have described that as just saying like 2 units to the left, 6 units down, or, you know, done the classic x comma y mapped to x minus 2 comma y minus 6, right? If I wanted the transformation rule. Let's see. Oh, let me color that in. Ooh, that was ugly. Let's see. Let me try again. All right, that one and that one are congruent. Any others? Any other claims to congruence? What are our thoughts? Yes. Aiden. Okay. I dig it. So those are triangles. Now, let's see. You said MKL? Okay. Is congruent to triangle which? How did you label it? Jeff? Okay, yeah. Now, this is actually really valuable and important. The way that I label the first one, I want the labels for the other one to correspond. So angle M, I think you agree, was congruent to angle G. So I want those in corresponding positions in their name and not just with respect to the drawings when I think about them, okay? So let's see. So angle K was congruent to which angle, did you guys think? Yeah, angle E. So you see that? So I want to correspond those. So I actually really like that you naturally kind of chose to name it in an order that those lined up. So I also could have rotated, I could have cycled through these. If I wanted to call this KLM, what one would triangle KLM be congruent to? Let's see. So K was the first one. So E, F, G. So there's actually quite a number of ways. There might be 6 different ways of labeling that. I might be wrong. I'll have to look back at the permutations later. But yeah, whichever name I pick first, I have to commit to that. Man, that's the ugliest E. It's okay, E. It's a Friday. Sorry. But yeah, so the sequence that I label it should correspond so that the corresponding parts are congruent. So angle M was congruent to angle G. Angle F is congruent to angle L. Angle E is congruent to angle K. The sides are corresponding and congruent, right? All of those goodies, triple tick marks right there. Yeah. So good stuff. So yeah, when we label them, we want to have those corresponding parts be congruent. Let's see. Here we go. Congruence transformation. Oh, I just want to like look at this again. I like that. Look at those colors. I love it. Let's see. Another name for rigid motion or a combination of rigid motions is a congruence transformation because the preimage and the image are congruent. The terms rigid motion and congruence transformation are interchangeable. How wonderful. Wonderful. Okay, here we go. Pick it up a notch. Example dose. All right. Describing a congruence transformation. So let's see. Describe a congruence transformation that maps parallelogram. That's what that shape is. Abacad to parallelogram. All right, there we go. So, all right, we got, man, some interesting stuff here. Anyone see a composition of transformations? I don't see a single one that could do it. I think it's going to take 2 steps. Anyone see a 2-stepper? Sorry, what? Let's see. Well, both of those, I would imagine, would map back onto itself. I'm thinking this. What if I drew this guy right up here as a mid-step? Okay, so we're looking at, you would describe that as, let's see, we're starting at A, B, C, D, and so that would have reflected over here, okay, over the y-axis. So reflect over y-axis as step one, and then step two, what do we do? Yeah, translate. Looks like down 4. Over the x-axis first. That would have been facing this way. Or sorry, wait a minute. Okay, it would have been like this. Oh yeah. Yep. So over the x and then translate that way. Yeah. So there are multiple solutions to this. I like that. Yeah. Good thinking. All right. Cool. So that's a way that we could do that. I think you guys agree. Ooh, here's a theorem. This is the one that you guys were exploring using Geometer's Sketchpad earlier. You guys are geometricians now. I like geometrician better than a geometer. Like, I guess I mean, yeah, algebratician versus algebra. A mathematician versus a mathemeter. Yeah, I don't know. Well, I don't know. I think I actually made up the word geometrician. I just like the way it sounds. Yeah, sounds good to me. So check this out. Reflection in parallel lines. Oh, this is a theorem. Guys, it's a theorem. Wow. Put this in your toolbox for later. Oh, look it. There's even a proof on page 206. All right. So it says this: if lines K and M are parallel, affirmative, yep, then a reflection in line K, all right, so here we go, reflect over K, bam, believe it, followed by a reflection in line M, whoop, is the same as a translation. What? Double reflection is the same as a translation? Okay. All right, so do you guys see how I could have mapped B over to here and A over to here, and that those two would have been congruent with each other? Yeah, I think so. All right. I think I believe that. Or maybe I should be a little bit more skeptical and have waited to believe that until I saw this proof. Yeah, that's what Exploration 1 was about. You guys were dabbling in that, and perhaps you discovered something on your exploration. I don't know. Let's see. Here's some other facts. If A double prime is the image of A, then A double prime is perpendicular to K and M. All right, you guys verified that. You saw that when you were exploring with your adventure hat, Indiana Jones style. So you want me to sign that pass?
Thank you.
All right. So and check this out. A double prime, the length, not the segment, is equal to 2D, where D is the distance between those parallel lines. Did any of you guys get far enough to come to that conclusion with the exploration?
Of course.
Yeah? All right. So if this distance is D, they're claiming that the entire distance across is 2D. Wow.
Two-dimensional?
Well, actually, yeah, both, in fact. Let me label this. What is this segment congruent to? If I label this point, I don't know, Q. So BQ is congruent to what? QB prime. It's also congruent to this one here and here. I agree. Yep. But I'm just working on this one line. Okay, so those two are congruent. How about, let's see, let's label this point S. B prime S. What's that one going to be congruent to? Hey, so all right. B prime S is also going to be congruent to what? B double prime S, right? This one right here. So notice that. Yeah, B double prime, yeah. Yeah. Yeah, kind of. Actually, this prime notation shows up again in calculus when you're doing first derivatives and second derivatives. Oh, it's wonderful. Wonderful. So guys, notice that the distance for D happens to be a single tick mark and a double tick mark length. And the distance from B to B double prime includes this piece and this piece, which were the same as those two. So I think like you can kind of see like, all right, yeah, it's twice the length across. I think, you know, so there's kind of like a visual suggestion for its justification, like so. I'm Mr. W. Is that what you, what? Yes, question? Yeah, question? No? You're just like, okay, you're with me. You're tracking with me is what you're saying. All right, I gotcha. All right, let's see. Using the reflections in parallel lines theorem, in the diagram, a reflection line K maps to blah, and a reflection line M maps to blah, blah. Also, HB is equal to 9. Where's my HB? This one right here, nueve. Let's see. Oh, let's see. I've been practicing my curly braces. Look at that. Oh, wow. Guys, let's just, moment of silence. Just, a round of applause. I can't stay silent. Look at that. Wow. Wow, look at that. I've been practicing. What can I say? That's a 9. I'm sorry. I'm not now. But my curly brace or bracket, I don't know. But actually, and we also know that DH double prime is equal to 4. Where's my DH double prime? That's equal to 4 right here. Nah, that one doesn't get a round of applause, but that's 4. Okay, name any segments congruent to each segment. Who's congruent to GH? Let's see, let me get my colors here. So for part A, GH is going to be congruent to whom? Let's see, GH is going to be congruent to G prime, H prime. Right, do you guys agree that to that? Yes. That's also going to be congruent to whom? G double prime, H double prime. Man, I love it. Yeah, because those are rigid transformations. Makes sense. B, question. Does AC, the number, equal BD? Let's see. A to C, is that equal to BD? Yes. Yes, they didn't. Oh, they did ask us to explain. Yes. Because parallel lines are all points on parallel line equidistant. Yeah. Are equidistant. No.
Wait, but when we think
it's got the little triangles. I think somewhere it said it. Well, it implied it there.
Oh.
But you're right. It didn't kind of have it in the given. That was a good call. You don't want to believe it just like willy-nilly. So yeah, so it was also had the little triangles indicating the parallelity of them. So parallel lines are equidistant at points, I don't know, perpendicular, whatever. You get the idea. Yeah. All right, there's your explanation, friends. Let's see. And C, what is the length of G double prime? G to G double prime. Okay. Thoughts?
Yes.
Well, this is going to be congruent to that. This is going to be congruent to that. So this is 4. This is 9. Segment addition postulate. What is H double prime equal to? 18 plus 8, 26. And I think that should be the same distance as that. So I'm going to say G double prime is going to equal 26. You guys believe it? Well, please do. Please. Just believe it, guys.
No more proof.
Well, meh. All right, let's see. Exploration 2, we didn't get to finish, but this one's going to be interesting. I don't know if you guys would have seen this one coming, but here is another theorem right there. Theorem 4.3. All right, wow, look at all those arcs and... let's see, let's see, the last what? The part C? Yeah, I said G double prime is equal to 26 because H double prime added up to 26, and those are going to be congruent to each other. So 9 plus 9 plus 4 plus 4. Right? All right, theorem 4.3. Reflections in intersecting lines theorem. So these are non-parallel lines, which is really the only other alternative unless we're talking about three-dimensionally skew lines or something. So it says lines K and M intersect at point P. I believe it. Then a reflection in line K. All right, so here we go. Wop, wop. All right, there we go. Right. All right, so these would be equidistant. Those would be equidistant. I agree. I believe it. And followed by a reflection. I can't sign my name while I'm speaking, I guess. I don't know what happened. Followed by a reflection in line M is the same as a rotation about point P. So double reflect. Right, double reflect. Like so, is the same as a rotation about point P. And here's the interesting claim. If this angle is x degrees, they're arguing that the angle of rotation between AB and A double prime, B double prime, man, I just love B double prime, is going to be 2x degrees for the entire angle. Let's see, let me see if I can draw that a little bit nicer. There we go. So that angle is 2x, twice the angle of the intersecting lines. There's a proof waiting for you right there. That's interesting stuff. I think so. Do you guys think so? No? Let's see. We've got one more example. Let me just prep it for you. Ooh, I love this. This is like a flippy floppy fish. You guys see the flippy floppy fish? Mine's in color at least. Let's see. So let's apply this using the theorem. All right. Okay, using the reflections in intersecting lines theorem, in the diagram, a figure is reflected in line K, flop, and the image is then reflected in line M, flip, and describe a single transformation that maps F to F prime. So this angle is 70 degrees. If I wanted to map that fish over to here using a rotation, what do you guys think that angle would be? So I would say angle FPF double prime has a measure of 100, or I'll just write this 2 times 70 degrees. I'll make it look like we at least did some math today, which is going to equal 140 degrees. I don't know why I wrote it that way. So there we go. Hundo 40 degrees. Not that bad. All right. Are we cool? Yeah? You guys believe it? Maybe? Well, maybe you'll have to prove it someday. So thanks for watching, Internet friends. Tienen un día al más bien del mundo. Go flip a fish.